Let us start. So last time we started talking about the following process. So consider E plus, E minus. So electron and positron, they scatter, and then they will annihilate, and then they create some other particles. Okay, so B and B bar are some fellow particles. Okay, can be different kind of things. So if we draw the Feynman diagram with the time going up, and then the process will be like following. So the initial particle. So this is E minus, and this is E plus, and then we have B and B bar. Okay. So we can So such a process is a very important discovery machine for new particles. Okay, very important. For discovering new particles. So let me just mention two examples here. So in 1974 to 1976 at SLAC, so SLAC is called Stanford Linear Acceleration Center. So they have an electron and positron collider. And so there they first discovered the tau particle. Okay, and this tau particle with mass is the 1.8 GeV. Okay, so when they when your total energy is greater than this twice the 1.8 GeV, then you can in principle create this tau plus and tau minus. And another example is in 1974, again at the SLAC, and the E plus, E minus goes to CC bar. So C is the charm quark here. Okay, it's the charm quark here. So what they observed is the bound state of the CC bar called J psi. So, and the mass of the J psi is about 3.1 GeV. Okay, 3.1 GeV. So this J psi, so this particle was discovered at the same time at Brookhaven through the proton through the collision of the protons by our own colleague Samuel Tin. And then they both get the Nobel Prize in 1975, I think. Okay. So there was actually a funny story regarding the discovery of this particle. So at Brookhaven, they collide the protons on with a fixed target. So that is a much massier machine because proton contain lots of contain quarks and gluons. And so, it's with strong interactions. So if you create a high energy, if you collide high enough energy, you can create any particles. But since involving strong interactions, and strong interactions have many particles, so the collider at Brookhaven is very, very massive. Okay, so in order to find the new particles, it's very, very difficult. Okay, but they manage find this new particle at Brookhaven. But Samuel Tin was famously extraordinarily meticulous. Okay, so he wanted to be absolutely right. Okay, so he was checking and checking. So during one of the so this is a rumor. So the rumor said that during one of the checking process, and somehow the rumor spread it, that he discovered a new particle. And so the person who was doing the experiment at SLAC then called him up. Even the rumor, so the news leaked even leaked the energy scale of the particle they found. Okay, and then the person was doing the register at the Slack, then called the Samuel Ting. He said, "Oh, I heard you have found a new particle." Samuel Ting said, "No, I didn't." Yeah, because he didn't want to have the. Yeah, actually, it's not very good because I'm recorded. I recorded, so I think this maybe it's not good to spread rumors. If it's not recorded, actually, I can tell the story. Anyway, so accordingly, and then the register and then you didn't find the particle, then I can discover it. Because they already knew the energy scale. They already heard the rumor of the energy scale. And this is a very, very clean machine. So electron-positron, when they collide, only energy created. So you don't create a lot of junks. And if you add the right energy, you can immediately find a new particle. You don't need to do much work. And so they put the machine at that energy. Immediately, new particle was discovered. Okay, and so they were so they were awarded the Nobel Prize jointly. Anyway, so this was an important discovery because before that people didn't believe quarks exist. Okay, even though people didn't quite believe the quark existed, even though there are many models, etc., and there are lots of other evidences. But this was the first. Because C quark is very strongly, it's very heavy, and so C and C bar they bond not very strongly, and so this is the first evidence, a direct evidence actually quark existed, and so this actually shocked the community. So this was discovered in October, so they call it the October Revolution, and played a very important role in understand. For people to accept the existence of quarks. Anyway, so in particular, by looking at the more general process, so this goes to hadrons. Okay, you just collide them, and then you look at it's going to hadrons. You can show that the quark have 3 colors. Okay, can show quark have 3 colors. And so we will see that. Okay. So before doing that, let's first have to do a calculation. Okay, so we have to calculate this explicitly. Let me see, I get my page a little bit. Right. Okay, so first we have to do a calculation. We have to calculate this process, okay? So after we have calculating this, then it's obvious that how that this can tell us why the quark have 3 colors. Okay. Yes?
So since you only see the bound state of the quarks, how can you know for sure that they are the bound state of the quarks?
Yeah, so indeed for the so that's why for many years, if you look at the proton and the neutron and the pion, they're very tightly bound, and so even though there were models about the quarks inside there, so it's not quite but in the C case, C are very heavy, and so they form a weakly bound state. And so in the sense that you're looking at so here it's in the sense you can look at the C quark, because it's a very weakly bound state of the C and C quark. Other questions? Yes.
Is weakly bound implied physically larger?
A weakly bound, you just say you can probe the. You can essentially probe the internal structure much easier.
If electron colliders are much cleaner than hadron colliders, then why does like the most important machine right now is like the hadron collider?
That's a good question. Because electron electron collider is more difficult because you have to build a straight line, and because the electron have a much stronger synchrotron radiation if they are moving in the circle, and so that loses lots of energy. And so that's the electron collider. They should build a straight line, but straight line you cannot have very high energy. Require very long distance, and so that's why normally people build the proton collider, which is easier, and yeah, it's easier to get higher energy, and but the next generation of the accelerator after AHC, people are talking about building an electron collider again. Yeah, yeah. Good. So now let's try to calculate this. Okay. So, and essentially we need to calculate this diagram. And yeah, this diagram is very easy to calculate. We need to calculate the cross-section corresponding to this. So let me just label a label. So this is E minus, so this is E plus, so this would be B, and this would be B bar. So let me label the momentum. So here, let's take P1, R1, and then this would be P2, R2 bar. So tell you this is an antiparticle, and so this one is K1, S1, and this one is K2, S2 bar. Okay, and so the amplitude for this will be M, but the cross section. So now suppose we consider unpolarized process. As we discussed last time, that the cross section, yeah, say the sigma, the omega, should be proportional to the spin. So we should sum over all the fellow states, sum over the polarization of the fellow states, because we don't measure individual polarizations, but we also should average over the polarization of the initial states. So the result, as we discussed at the end of last lecture, is that you need to take 1/4, come from the average over the spin of these two initial particles, and then just sum of spins of all the particles. Okay. Okay, and right. Okay, so that's the thing we need to. So let's just try to first compute the M. So M is given by. Okay, so we just follow our rule. So you follow the fermionic line. Okay, so here there's a vertex. So here there's a gamma. So each vertex gives you minus I E gamma mu. Okay? So if you follow this one, okay, then we get V bar R2 P2, then minus I E gamma mu, and U R1 P1. Okay? So this is coming from this fermionic line, and from this fermionic line, we start from here. So this would be the U. Yeah. Also, we have this propagator. Let me just write down the propagator for the photon. So let's take psi equal to 1 gauge, Coulomb the Lorentz gauge with psi equal to 1, and then let's follow this line. So here we should have a vertex gamma nu, okay, and then we will have U bar S1 K1, then minus IE gamma nu V S2 K2. Okay, so this is the full amplitude. So this is a number. Okay, so this is a number because this is a row vector. This is a matrix, and this is a column vector. Okay, so this will be a number. And similarly, this will be a number. And then the mu nu in this is contracted with the propagator of the photon. Okay. So actually, if I want to be precise, there's actually a factor of I here. Okay, yeah, but this factor of I is not important because and then the Q. So the Q is the momentum of the photon here. So the Q should be the sum of the initial momentum. Okay, so Q is should be equal to P1 plus P2. And also this means that the Q square is equal to minus S. Okay, remember S is defined to be the minus P1 plus P2 square. Okay, so now we can write this amplitude using a shorthand notation. So if I forget all this momentum dependence, and then this is equal to minus IE square divided by S. Okay, if you cancel all the i's, and then we have two terms, V bar R2, gamma nu, and U R1, and the U bar S1, gamma nu, V S2. Okay. And now we need to, then what we need to do is we need to square it and sum over all the spin, and then we plug the resulting expression into the formula we derived for the cross section we derived last time. Okay. So so the whole calculation is a little bit tedious. Okay, but I think we should at least go through one such calculation, because this is the kind of prime example, okay, of QED calculation. So each of us should at least see it once in our life, okay? So we will do it explicitly here.
The final line needs a metric too. The final line needs a metric.
The final line is a metric. You are right, but I can do that. Just put the gamma mu here.
Do we need to keep the I off?
Oh, okay, yeah. Also, here, because the Q square is never equal to 0, so we don't need to care about epsilon. Okay, good. So now let's do the square. So square, we just square this term and square this term. Okay. So when we square this term, so we also square this term. So here we just get the e to the power 4 divided by s squared. And when we square this term, we just get another, so this is gamma nu, gamma mu. So if we square it, then we get another term. Okay, so we just copy this term. Yeah, let me just copy here. You are 1. Yeah, when we square it, we get another copy of this. And so let me just write it. Yeah, sorry. So we take the complex conjugate, okay? So when we take the complex, we need to take the modulus. That means we need to multiply this with its own complex conjugate, okay? And the complex conjugate of this is given by U bar R1, then gamma nu, and V R2, and then times this one and its times its complex conjugate, and so we have U S1 bar gamma mu VS2 and VS2 bar gamma nu US1. Okay, so this is the original copy with the nu contract with this nu, and this is a complex conjugate with this nu contract with this nu. Okay. Good. So this looks like a mass. Okay, looks like the big mass. And it turns out actually there's a series of beautiful tricks we can use to calculate this quantity. Okay, so naively you say, oh, to calculate this thing, I have to plug in the individual wave functions for this v and u, etc. Okay, we worked out before, but fortunately, actually, we don't need to do it. Okay, so we can actually go through a series tricks, and that we don't have to do it. So the first trick is that this is a number. Okay, since this is a number, I can put a trace outside of it. Okay, because the trace of a number is just a number. Okay, and now you remember the trace have these cyclic properties. Okay, trace have this cyclic property, so I can actually move this to there. Okay, so I can move it. So now I can write it as equal to 4 s squared. I can just move this to there, so that the two R2 come together. Okay, so we have V R2, V bar R2, gamma mu, and U R1, U bar R1 times trace. Similarly, I put this US to the other side, US1, U bar S1, gamma mu. Sorry, I missed the gamma mu. Sorry, did I? So I put this. Oh, sorry. No. Sorry, I just missed that one. U bar R1 gamma mu. Okay. And similarly with that, so I have U bar S1 gamma mu, and then we have VS2, V bar S2, and gamma mu. Okay. So I get that. So the reason I do that, so now in this form, now this is a matrix. Okay, now this is a column, this is a row, and this is a matrix, and this is column, and this is a row. So this is a matrix times a matrix and times a matrix and times a matrix. Okay, and then you take the trace, in the end you get a number. Okay, similarly with things here. And then we need to sum over all the spins. Okay, remember we need to actually, when we sum all the spins, it means we sum over all possible, we sum all the R2, R1, S1, and S2. Okay. So now we can use a trick which we had when we discussed the Dirac spinors. Okay, so now recall. Now recall for unshelled spinors. Means those satisfy the equation motion. Okay, those all the unshelled spinors. Okay, they satisfy the following: sum over R. If you sum over all the R of the U, URP, UR bar P, that give you IP slash plus M. Okay. And when you sum over V, minus IK slash plus M. Okay. So now we see we have, if we sum over spin, then we have these combinations. Now we can use those formulas. Okay, now we can use those formulas. So now we find 1/4 when we sum all the indices R1, R2, S1, S2, the M square we get, then we just get the, so we get E4 divided by 4s squared. And then we just apply those formulas into here. Okay, so we get trace minus I P2 slash plus M. So M is the mass of the initial particle. And I take the M prime of the mass of the final particle. So the E plus minus have mass M, and B bar have mass M prime. Okay. So then I have this, then this times, then this gamma mu. Yeah, so this is still inside this bracket. IP1 slash plus M gamma nu. And then I have trace IK1 slash plus M prime gamma mu and minus IK2 slash plus M prime gamma mu. Okay? So I just, when I do this, so the spin sum is crucial, okay, for this simplification. When I sum over spins, and then without using explicit expression of those U and V, we can write all of them just in terms of P slash and K slash, etc. Okay? Any questions on this? And now we can evaluate the trace. Okay, so evaluate the trace. Now we need to use the various formula. I think some of them you have done in your P set. P set, now recall. So this is the place all those exercises, they become useful. So gamma mu. So here, yeah, if you look at the structure of these terms, so here there's a P slash. So there's one gamma matrix here. And there's another gamma matrix here. And here P slash is the gamma matrix here. There's another gamma matrix. So at the most, we can have the product of the 4 gamma matrices inside the trace. And also depending on the product, we can have 4, 3, and 2. Okay, 3 and 2. So we need to, for this purpose, we need to read those formulas. What are the product of the 4 gamma matrices inside the integral? So this is just given by eta mu mu, eta lambda rho, plus eta mu rho, eta mu rho, eta nu lambda, minus eta mu lambda, eta mu rho. Okay? And also if you have 3 gamma matrices, do you know the answer?
0.
Yes. Good. And if I have 2 gamma matrices, do you know what is this? That's right, it's 4 eta mu mu. Okay, so you can just apply those formulas to here. Okay, so I will not do the calculation explicitly. So you can just plug them in, and then it's mechanical. You can just calculate it, and then you find 1/4 sum over spin m squared is equal to, let me write down the answer. So even though this answer is slightly long, but I think it's instructive to write it down so that you see it. So when you plug all this in and do the algebras, and you find that the expression can be written as this: K1 dot P1, K2 dot P2 plus P1 dot K2 and P2 dot K1, the minus m square K1 dot K2 minus m square P1 dot P2 m prime square. Sorry, here should be m prime square plus 2m square m prime square. Okay. So we discussed before that the amplitude square must be a Lorentz scalar. Okay, must be a Lorentz scalar, and so you see it explicitly here. So it only involves either m square, m prime square, or the product, dot product of initial and final momenta. Okay, and you see all kind of combination of the initial and final momentum appearing here. And now, so it's convention. So as we mentioned before, actually, if you look at all these different dot product between initial and final momenta, actually, because of the momentum conservation, and actually there are only two Lorentz invariant. Okay, so it would be convenient to write all this in terms of those two Lorentz invariant. Okay, so that's the S2 two of the STU variables we defined previously. Okay, so it's often just to use STU at the same time. So we just yeah. Okay, so now if you write them in terms of STU, and then you find, for example, yeah, let me just give you some example. For example, 2K1, P1. So this can be written as T minus m square minus m prime square, okay, which is the same as 2K2 dot P2, okay, and 2K1 dot P2 then is actually equal to 2K2 dot P1 then equal to U minus m square minus m prime square. Okay. And then since related to the initial momentum, then related to the S equal to S minus 2m square and minus K1, K2 equal to S minus 2m prime square. Okay. So you just apply those equations in here, then you can write them in terms of STU variables, and then you find that 1 over sum over spin m square is equal to the following expression: QE to the power 4 S square T minus m square m prime square square plus U minus m square minus m prime square square plus 2s. Okay. So recall that s plus t plus u equal to 2. So you can eliminate one of them. Okay. So you can eliminate one of them. So this concludes the calculation of the scattering amplitude. Okay, so that's the expression you get. Okay, and you see that it's all expressed in terms of this STU can be expressed nicely in terms of this STU variables. Any questions on this? Good. So now let's calculate the cross section. And our goal will be to calculate the total cross section, okay? And so for this purpose, let's do the center of mass frame, okay? So let's go to consider the center of mass frame. Well, this is the simplest. So remember, in the center of mass frame, we So first we need to yeah. So remember the certain mass frame, you get that the d sigma d omega cm is given by yeah. Let me check my formula. Suddenly I'm not sure about the formula. Yeah. So it's given by, say, the m square divided by p cm prime divided by 64 pi square s pc prime. Okay, so PCM prime is the momentum for the final particles, and PCM is the momentum in the center of mass frame for the initial particles. Okay. So now we also need to find the PCM, etc. Okay. We also need to express the m, the amplitude in terms of the center of mass square. Okay. So in the center of mass frame, then we have the P1 would be, say, E PCM. Okay, the P2 will be equal to the same E, but minus PCM. Okay, they have the same E because they have the same mass. Okay, similarly, K1 would be E prime PCM prime, and K2 would be E prime and PCM prime minus PCM prime. Okay? So now, from energy conservation, you immediately conclude that E must be equal to E prime. Okay? So I can forget about E prime. Okay? Because the total energy will be 2E, and the final energy will also be 2E. So E have to be equal to E prime. And then we can find, and so E would be equal to 1/2 square root S. Okay. So this is the yeah, or S is equal to 4E squared, because the P1 plus P2 is just 2E. Okay, you square it, become 4E squared. And then we find the PCM square equal to then S divided by 4 minus M squared, and the PCM prime square equal to S equal to 4, S divided by 4 minus S prime square. Okay. Any questions on this? Yes?
You know that the first component of your formula, they have some to but how do you know that it exactly has to split between two particles?
Sorry?
So how do you know that the final state particles have to have the same energy?
Oh.
Like you know that there's some has to be two.
Yeah, because they have the same mass.
I see.
Yeah, because their momentum are opposite to each other in the center of mass frame, and they have the same mass.
But you can allow for your final particles to have different masses and then the switch.
Yeah. If they have, but in this process, we are considering there always particle and antiparticle. It's an annihilation process. We always create the particle and antiparticle. So other questions? Okay. So you can similarly express the T. Okay, you can similarly express the T and U in terms of this center of mass, the momentum, etc. Okay, and so I will. You can just do that. Okay. So let me just write down the final answer. Let me just write down the final answer. You can also rewrite 1/4 some spin m squared equal to, in terms of the center of mass, and then you can write the and then you find it's equal to e to the power 4 and 1 plus m squared plus m prime squared divided by e squared plus PCM squared PCM prime squared cosine theta. Okay, and the theta is the, so you have the scattering of the initial particle with PCM, and then you have the final particle with the PCM prime, and so this angle is theta. Okay, this angle is theta. And so the theta comes from when you calculate using the involving T and U. Okay, involving T and U. And so now you have we have everything. So we have the PCM. It's all in terms of S, and then your amplitude is also expressed in terms of the either S or E. Yeah, E is also the S, and then we have the theta. Okay, then we have the theta. So you just plug the whole thing into here. Okay, just plug the whole thing into here, and then you find the total cross section. Okay, it's just the d sigma d omega center of mass frame, and then sin theta d theta d phi. Okay, nothing here depends on phi, so the phi integral you can just done trivially. And then you just need to do the theta integral, and then you have this. Okay. So again, let me just write down the final answer. So in the end, you get 4 pi alpha square divided by S. So the alpha is the fine structure constant. Yeah, so the alpha is E squared divided by 4 pi. Is the fine structure constant, and this is 4 pi alpha squared, 3s, and then 1 minus m prime squared divided by E squared, 1 minus m squared divided by E squared, and the whole thing times 1 plus m squared divided by 2e squared, and 1 plus m prime squared divided by 2e squared. Okay. So this is the final answer. Okay? And this is the answer you can compare with experiments. Okay, so this is the answer you can compare experiments. Any questions? So now if you look at this answer, it's almost completely symmetric in terms of n and n prime, okay, except that for this ratio, and the m is downstairs and n prime is upstairs, okay. Otherwise, it's the, yeah. So this n prime is upstairs, of course, it's the, do I have the, yeah. Good. Yeah, so this factor is key. Okay, you have to have such kind of factor in the upstairs, because when E, you have to be E to be greater than n prime square in order to produce the particle. Okay, if your energy is not big enough to produce, in order to produce B and B bar, your energy at least. So each each E has to be large enough to be the greater than M. Okay, because your QE total energy must be greater than 2M prime. Okay, and so you see that when E is smaller than M prime, and when E equal to M prime, and then this factor becomes 0, and then the cross section becomes 0. Okay. Any questions on this? Okay. So now let's consider some specific cases. So now let's consider E plus, E minus going to muon. Okay, so the muon is the next massive lepton after the electron. Okay, so in this case, say m square will be me square, and m prime square will be m mu square. Okay, and m mu, so the muon mass is 207 MeV. Oh no, it's the no, it's the 100. Actually, I didn't code the number. So muon mass is 207 times the mass of the electron. Okay. So do anybody remember the electron mass? Yeah, that's right. Yeah, 0.5. 1? Did you say 1? Yeah, it's 511 keV. Yeah, 0.511 MeV. And the muon is the 207 times the mass of the electron. So if you want to create the muon, then the initial total energy, okay, so the S, so the square root S, which is 2E, have to be greater than the 2 m mu. Okay, so that means that the E has to be greater than m mu. And then this is much, much larger than the electron mass. Okay? So this is about 200 times larger than me. So that means actually that for all purpose, that you can just neglect the electron mass. Okay, and so this ratio is a huge. So this ratio is tiny. Okay, it's tiny. So we can treat essentially the electron as massless. Yeah, it's just not well defined. Yeah. No, you don't even. Yeah, in this case, you don't even go to that. So in the case that the let me see. So in the case that the let me think a little bit. Right. So yeah, for this case, of course, it's not well defined. But in the opposite case, let's imagine if you have the two very massive particle to collide to create, say, lighter particle, and then in that case, actually, I don't remember the answer from my top of my head. Yeah, it's a good question. I will try to find it afterwards. Any other questions? Okay, good. So in this case, so when the electron mass is much larger than when the muon mass is much larger than electron mass, and then we can set essentially me equal to 0. Okay, and in this case the formula becomes simpler. And in this case it becomes similar. The downstairs equal to 1. And this factor also become 1. Okay. This factor also become 1. So then there are two interesting regimes. There are two interesting regimes. So the first is you just near the threshold. Okay, just near the threshold means that the PCM prime is much, much smaller than mu. Okay? So in this regime, then the E would be approximately just mu. Okay? And then S would be approximately just 4 mu square. So now if you just look at that expression, yeah. So let's look at that expression. Then you find Then you find that the total, the differential cross section is equal to alpha square equal to 8 mu square, and then PCM prime divided by mu plus higher order corrections. Okay, so you expand in PCM divided by mu. Okay, PCM prime divided by mu, and the total cross section just given by pi alpha square 2 mu square and PCM prime divided by. Okay, so here you see explicitly that when you reach the threshold, the threshold corresponding to this quantity goes to 0. Okay, so when this quantity goes to 0, and then you the cross section go to 0. Okay. So another regime of interest is the ultra-relativistic regime. Ultra-relativistic regime. So in this case, which we can take E to be much both than ME and mu. So also much greater than mu. Okay. So of course it's already much greater than ME. So in this case, then we can you can just here. You can just essentially take the both mass to be 0 in this case, and then you find in this case that the d sigma d omega Cm just given by alpha square divided by 4s. Okay. And then you can find the total cross section. So you can find the total cross section given by four pi alpha square divided by 3s. Okay. So now this final formula is very simple. So you could have written down this formula without doing any calculation, of course, up to the prefactor, just on dimensional ground. Okay. So in the ultra-relativistic regime, then essentially you can neglect both the mass of the initial particle and the final product. And then in this whole process, if the initial particle is massless and the final particle is massless, and then for this whole process, the only scale is what? The only scale is S. Okay, that's the only scale. So the only scale is S, and essentially, and then that means, and this should have dimension area, okay, and then that means that there should be 1 over S, okay, and then alpha square just come from because we have 2 vertex, okay, and from a tree level process. Good. So good. So if you draw the plot, say often if we draw the total cross section times S, so S times the total cross section as a function of the square root S, then the threshold is at 2 mu, 2m mu, and then here it goes 0, like a square root, and then you go into, say, approach a constant. This is 4 pi alpha square. Okay, so you have a curve like this. Okay. So now let's consider. Using this process to show that actually the quarks have 3 colors. Okay, the quarks have 3 colors. So for this purpose, let's consider E plus E minus goes to hadrons. Okay. So this seemingly is a very complicated process. Okay, seemingly this is a very complicated process. It's because so suppose if you have E plus, you create a quark and the anti-quark pair. But you remember the quarks, they're confined. Okay, so we don't observe individual quarks. It's because the QED is strongly interacting, and so the quarks are confined inside the proton, pions, etc. And so in this process, so even though originally created the quark, but each individual quark and anti-quark, they cannot survive on their own. So their presence will polarize the vacuum, create many other particles. And so what happens is that you create so each of them will create lots of particles along with them. Okay, so in the end, it's a complicated product. You observe many hadrons. Okay, you observe many hadrons. And then of course in the detector we don't directly observe those quark and anti-quark. We just observe those hadrons. Okay. And so this is then you say how do we in any hope to be able to understand this process just by measuring this very complicated product, because this product can have protons, neutrons, pions, can also have other things. Okay. And then this is a very complicated process. But now the key is the following. Indeed, if you look at the question of going to each individual hadron, is complicated. But if you consider so-called inclusive process, which goes to all possible hadrons in this process, okay, and then that probability just given by the total cross-section. Okay, remember the total cross-section just measures the total probability to create such particles, and then when they are created, and then they go through a complicated process, but that process is unitary. Will be or probability 1 to go to all possible fellow product. So if we include the cross-section going into all possible fellow product, and so that probability just captured by the total cross-section. So the total cross-section for this process, okay, for the E plus E minus going to QQ bar, and then just including the total cross-section, so inclusive section for all hadron product. Okay. So this way we can actually measure this process. Okay, indirectly. Okay, even though you don't directly measure the quarks. So now let's calculate the total cross-section. Okay. So now let's calculate the total cross-section. And now we also don't have a choice which quark will be produced. So we need to sum over the total cross section for E plus, E minus goes to, say, different kind of quarks. So I corresponding to different types of quarks. Okay. And so each of them we can just write it down using our formula. So the only difference, okay, the only difference. So the same diagram applies. The only difference is that the quark have different charge from the electron. So here is IE gamma mu. Here we should use the charge for the quark. Okay, so that would be IQE gamma mu. Okay, Q would be the quark of the charge compared to the charge of the electron. Okay, so then what do we get? Okay, so suppose Qi is the charge for the quark Qi, and then this give you. So this total is going to all hadrons. Okay, to all hadrons. So then this will be given by sum over the number of colors. Okay, and C is the number of colors for each quark. And then the I will be the flavor. Now the I is the flavor of quark. Say whether it's the U quark or D quark or charm quark, etc. And NC is the number of colors. And then you have Qi square. And then you have sigma E plus E minus Q mu plus mu minus. Okay, the rest is the same. So for each type of quark, this is exactly the same. You just replace this vertex by IQi, and then you get the Qi square. Okay? Good? Yes?
So you talked about how like when the quarks hadronize, they polarize the back.
Yeah.
Just a very small mini intuition on what that process is like, or you can even calculate out the possible.
No, that's a very complicated process. We cannot. Yeah, that's a very complicated process. It's a huge field. Yeah, to study that. Yeah.
But then how do you account for all possible outcomes if you're probably accounting for the possible quarks?
No, you just measure you just measure all possible products, right?
But here you're just sending over the flavors and the quarks, right?
No, that's the only thing you can produce.
And then you're not worrying about like the final states that happen from these quarks.
No. As I said earlier, we only need to worry about this process, and then this process into hadrons is complicated. But this happens with probability 1. Okay, and so if we calculate this probability, then we know the total probability to here. Yeah, because this happens with probability 1. Yes. Yeah. Indeed, that can happen, but this is the leading process. Yeah, this is the leading process. Yeah, so this is the leading approximation. Yeah. Other questions? Okay, so now you just given by this formula because you just multiply the Qi square to the total cross section of the E plus E minus to muon, and then you sum all the flavors and times the number of the color. Okay, times the number of color. Okay. Because all different colors have the same charge. Okay, all different colors have the same charge. So So now we can define a ratio. So this is the same for everybody. So this just factorize. So we can define a ratio called the quantity called R. Called R is defined by sigma E plus E minus goes to hadrons divided by sigma E plus E minus goes to mu plus mu minus. And this is just given by sum NC times sum over I flavor and the QI square. Okay. And this I, of course, you should only sum over I which allowed by your energy. Okay. Those quarks which are too heavy will not be created by your energy. You're not including the sum. Okay. So flavor of quarks allowed by energy. By initial energy. Okay? If the quarks are too heavy, then of course you cannot create them. So now let's list. Now let's list the quarks we know. The process, I will not do the final one. So we have U quark, D quark, strange quark, charm quark, bottom quark, and then there's a top quark. The top quark is very heavy, and its process will be communicated. So let's not worry about that. So then the charge for each of them. So this is 2/3. So this is minus 1/3. This is minus 1/3. This is 2/3. This is minus 1/3. Okay. And then the mass, twice of the mass. So I just give you some rough number. So U would be about a few MeV. Okay, so this is a few MeV. So this again is a few MeV. Just a few MeV. Okay, so I will not. And so the strange will become, strange is heavier twice. It's 190 MeV. Okay, and the charm, the threshold is about 3.1 GeV. And the threshold for the bottom quark is about 9.5 GeV. About 9.5. So now let's consider the value of R as a function of energy. Okay. So then, if you consider for S smaller than the charm, say 3 GeV. So in this case, we can just produce UDS. Okay. So in this case, we have R equal to NC, then times, say there's 1 2/3 and 2 1/3. So we have 3 square plus twice 1/3 square minus 1/3 square. Okay. So this is give you NC times 2/3. And then because others you cannot create. Okay. And for square root S, say between 3 GeV and 9.5 GeV, the threshold for producing the bottom quark. And then you can create the charm quark. So you just add another 1/3. So, and then now R become NC times 10 divided by 9. Okay, just add another 2/3 square here. And then for now, if you have square root S greater than 9.5 GeV, and then R. Now you can create the bottom now. Okay, then you add another 1/3 square. So this R equal to NC times 10 divided by 9 plus another 1/3 square. So that gives you NC 11 divided by 9. Okay. So now if you plot the R as a function, say for square root S, as measured by experiment, okay, so you should see a threshold at 3, another threshold around 10, yeah, 9.5, say around 10, okay? And then you see something like this. Yeah, I'm just drawing roughly. Okay, you create something, and then you something, and then you have another threshold, and then you have another threshold. So it turns out the first 9 is precisely at 2. Yeah, I have to say precisely is just say up to some error bar. Okay, and the other one is about say a little bit more than 3. And yeah, and yeah, a little bit more than 3, and then the 4 is around here. Okay, 4 is around here. Yeah. Anyway, so if you compare with these numbers, and you conclude that NC is actually exactly 3. Yeah, NC is 3. Okay, to be compatible with this experiment. Any questions on this? Yes.
Does this mean that this is the dominant process for
Yeah.
electron-positron?
Yeah. Yeah, going to hadrons. Yeah. Other questions? Okay, good. So this way, so this is a very nice, simple. Even though this is a very simple process, but actually have very important physical implications. Okay, and in fact, quite profound physical implications. Yeah. So we only have a few minutes left. So let's say a few words regarding the next topic. Okay, so let's again consider this process of E plus, E minus going to mu. Okay, going to mu. And then, so we have again this diagram. Okay. So suppose this is P1, P2, and K1, and K2. So when we draw this diagram, we take the time as going above. So these are the initial state, these are the final state. Okay. So now if we view this diagram sideways, say if we view in this direction, okay. So if you try to think that the time going to that direction, say if you try to view it sideways, and then in this case viewed sideways, okay. And now this become an initial state. So this is still initial state, and this is still initial state. Let me see. Let me see. 1 second. Let me see. Right. Sorry. Yeah. If you initial view sideways, and then this is the initial state, and this is the initial state. Let me draw the arrow this way. Okay. So that because the it doesn't matter. Let's draw the arrow this way. So that this is the mu. This is the mu plus. Okay. So let's now let's view this way. And now this is look like you have initial electron, and then you have initial muon. Okay, and then this become a process E minus plus mu minus going to E minus and mu minus. Okay, because this is the final particle. Now going out will be the particle, and this final particle going out will be a particle, and then the final will be the electron and the muon. Okay. So and then you get the process B. Then with the diagram, when you view the sideways, then you have a diagram like this. If I draw using our again time going to up, then this is like that. Now this is E minus, mu minus, and mu minus. Okay. So now you wonder whether there's some relation between these two processes. Okay. Whether there's some relation between this process from you just exchange initial state to the final state. So it turns out actually there's a very nice relation between them. Okay, if you know one of them, you can try to deduce the other. Can help you deduce the other, which we are running out of time, so we will do it the next time.